BGE Physics. Welcome to another video revision lesson for Key Area 3 this time, for Key Area 3 Part 1. Alright, so we're going to go through the next one, which is called energy. Okay, so we're in the next key area, which is called energy. So some of you have been going through this and you need a revision lesson, so that's exactly what I'm going to do. So let's go ahead and do it. So what are we going to be looking at today? Lots of things. Energy, energy transfer, states of matter, and conductors and insulators of heat. So let's get cracking. So, energy, page 35 in your booklets. Follow along, write in the notes that you need to. Pause it if you need to go back, rewind it so you can understand exactly what's going on. Alright, so we're going to go through it. We're going to start with page 35. Now, energy cannot be created or destroyed, but it can only go from one form to another. Physicists find energy quite a difficult concept. A lot of them would say they don't actually know what energy actually is, but we know that it comes in different forms. And we're going to talk about the forms right now, okay? So we know that it can go from one form to the next, but what are the forms of energy? So pause the video, see if you can come up with 8 different energies and see if you can get them all. If you do, very well done. If not, I'm going to go over them. I'm going to give you 5 seconds to pause the video and see if you can get the 8 different types of energy. And you go. Okay, so if you pause the video, well done. And let's go over the 8 types, see if you got any right. Okay, so the first one is movement, which is kinetic energy. So it's the energy that you get from something moving. The next one's atomic, which is basically kind of the energy locked up inside atoms. You have chemical, which is in all your food or your batteries. You have heat, which is kind of either absorbs or it gives out energy. Okay, so that has different types, gives or takes. Electrical, obviously lots of electrical energy that we use day in, day out. Light energy, okay, from the sun, from the light bulbs in the room, whatever, anything that gives off light is light energy. Potential energy, okay, so in something that's high, it's got some sort of height above the gravitational pull of Earth, you'll have some sort of potential energy because it has the potential to drop, okay, due to the gravitational force. That's quite a hard one, but we'll talk about it in a second. And things like sound energy, all right, given out when objects vibrate, okay, so you obviously will be, have done music, so you will be very aware of sound energy, all right, so those are the 8 different types, and we can often put a mnemonic to that, saying Mac helps in order to get all the energies in our heads, and so we know each one, okay? Right, so if you were in class, you would be able to bounce a ball and we could show you a little experiment. But you could do this at home if you have a ball of some sort. And if you bounce that ball, you'll notice that when you bounce the ball, it will come back up, but it will not come back up to the same height, okay? But let's first of all talk about the energy involved. So when you drop a ball, all right, it will have some sort of kinetic energy, it will have some sort of movement energy. Now when it hits the ground, okay, that movement energy is no longer there because it's hit the ground. But in that slight moment in time, we actually have potential energy, okay? Because the potential energy builds up in the ball, the pressure going down and lifting it back up, but then as soon as it lifts off the floor, it's back to kinetic energy and it lifts it back up. And then it comes back up and it goes to potential energy again. All right, now this time the potential energy is based on the fact that it's gained some sort of height and the gravity wants to pull it back down again. So when it does that, it then goes to kinetic. And so you have the motion of the ball going down and up, down and up, down and up. Now, if we were to say that the ball doesn't come back up to the same height, which you will obviously be aware of, that's what happens in real life, why would that be the case? Now, a hint, okay, can you hear anything or can you feel anything when a ball is bounced? If you ever played squash and you hit a ball against the side, if you do it long enough and you feel the ball feels warm. Okay, and when you hit it, it sounds, you have a sound. When you bounce a ball, it has a sound. So sound and heat energy are also at play here. So all the energy is not going from bouncing it, coming back up and going to the same height, because if we did that, the ball would just bounce forever. But it loses energy in other forms, such as heat or sound, okay? So that's what we have when we talk about a ball bouncing. We would have done that in class. Obviously, if you've not seen that in class, that's how it works and that's how the experiment works, okay? So lots of things you can talk about when you think about energy. Right, so let's talk about energy transfer now, which is page 37. in your booklets. Now, looking back to space, if you've done space, great. If you've not, then don't worry. When we have something in space coming back into the Earth, we call it a re-entry. And when it hits re-entry, we see a lot of heat build up in the spacecraft. Now, we say that there's lots of heat in the spacecraft, and we know there's lots of heat in the spacecraft, but it's difficult to understand why. And so I would like you to pause the video and have a wee think. Why is there lots of heat that gets built up when a spaceship enters into the Earth's atmosphere? So pause the video and we'll go over it in 5 seconds. Okay, hopefully you managed to get a good answer for this. Okay, now basically when a spacecraft comes back in, it's going around about 11,100 meters per second. That's fast. All right. Now when it goes in, it's starting to hit the atmosphere. Now the atmosphere is made up of lots of particles of gas, and at room level, at me just walking around, I don't feel any pressure on my face when I'm walking or doing like that. But when you're going that fast, particles in the gas and in the air around us will feel very, very forceful when it hits your spacecraft. Okay? So what happens is that the particles start to collide with the spacecraft. And when it collides with the spacecraft, it creates friction. And friction, when you do this with your hands, okay, creates heat. And so the gas particles hitting the spacecraft get hotter and hotter and hotter until we basically have a very, very, very high temperature outside of the spacecraft as it enters into the Earth's atmosphere. Okay? So we have lots of friction. And so what we need is we need very heat resistant tiles to make sure that it doesn't burn up. Because if we just had like something like wood coming back in the atmosphere, it would just burn up. So we need something that's very heat resistant so it can withstand it can stand a very, very high temperature as it re-enters the Earth's atmosphere. Okay? So, same thing works when you have a parachute, except you're not already in the atmosphere, so it just has lots of air resistance going up the way, causing lots of friction, which slows you down as you descend, which is a good thing because you don't want to fall without a parachute. Alright, so let's now talk about states of matter. Alright, we're going very fast through this, and hopefully this is a revision exercise, but you can pause it, go back, have a wee look through things, but this is states of matter on page 39. Okay? So, we have 3 states of matter: solid, liquid, and gas. Okay, solid, liquid, and gas. Now, all of these states of matter have particles, but the particles act differently for each state. Okay, so let me show you a little, well, before we do that, what's worth knowing is, again, back to space, we often see that our planets have different states of matter itself. But the first 4 planets, called the terrestrial planets, have more of a solid structure. All right, they have a liquid core, but they have a solid structure, like rocks. That's why we can stand and we can like walk around. But if you go to the other planets, it's too cold, and so it has a gas giants. Okay, so they're more of a gaseous planet. So we even see in our solar system different states of matter. Now, when we have solids, liquids, and gases, the particles are rearranged in slightly different ways for each state of matter. For solid, we have them touching, but they're not moving. Okay, so it's a nice steady structure. For liquids, we have them touching, but they're a wee bit more loose and they're fluid. They're still touching, but they can move. And for gas, they're now not touching, but they're moving, and they're moving very, very fast. All right? So, just saying that, solid takes up a small bit, liquid then is a bit looser, and it kind of lies level on the flat there. And then we have gas, where all the particles are everywhere. Okay? And again, the same diagram: solid, nice and compact; liquid, slightly looser; and gas, they're all flying everywhere. All the particles are going everywhere. So, the key bit to take away though for solids, liquids, and gases is that solid particles are touching and not moving, liquids are touching and moving, and gases are not touching but moving fast. Okay? So lots of interesting things there, and I think that might be even a note in your booklet. All right? So let's take the example of water now. Okay? And we know that water has 3 states of matter: ice, water, liquid water, and steam. Okay? Ice, liquid, and water, and steam. So we know that it freezes at 0 degrees. When it freezes, it goes from water to ice. And when it boils, it goes from water to steam. And that's at 0 degrees and at 100 degrees. Okay? Now, when it goes to ice, heat energy is actually lost. Okay, it's getting colder, so heat energy is getting lost. When it gets hotter to steam, heat energy is gained. Okay, so it gets hotter, heat energy is gained. So heat energy is gained when you go from liquid water to steam, and heat energy is lost when you go from liquid water to ice. Okay, makes sense though. So, a wee statement here, heat energy is gained or lost by a substance when its state is changed. Okay, so that's a key point there. Now, heat makes molecules spread out and turn into a gas, just like we said moments ago with the water analogy, and also cold makes molecules squeeze together and turn liquid into solid. Okay. Right, a wee side note is that we also have another thing called a non-Newtonian fluid, so it's kind of separate from the states of matter, but it's kind of a liquid and kind of a solid. And what happens is that when you give it stress, when you shake it, when you hit it, when you do anything like that, it turns into a solid. But when you let it just nice and easy, let it flow, it becomes a liquid. Okay, when you don't do anything with it. All right, so one of these things, one prime example is ketchup. Ketchup is a non-Newtonian fluid. If you start hitting the bottle, trying to get it out, or vigorously trying to kind of squeeze it out, whatever, then what happens is that it just doesn't want to budge. It just doesn't want to do it. But if you let it slide and you're very gentle, it will move because it becomes a liquid. So it's a non-Newtonian fluid for ketchup. It's kind of why they're in squeezy bottles now, so you don't have to actually worry about the glass bottles. Now, last thing is conduction and insulation of heat. Okay, so heat, we talked about heat energy. Okay, heat energy can be gained or lost, but we also know that heat can transfer, heat can move. Okay, and we're going to specifically look now about heat moving through a solid. Okay, but we also know that heat goes from hot to cold. Okay, from hot to cold. So when you open a window, you don't actually get cold air coming in. You have hot air leaving, and so therefore the room's starting to feel more like outside because more hot air from inside is going out. So it always goes from hot to cold. So what we would do in class is we would do an experiment, and hopefully you may have done this, and we would have a candle, or we'd have some sort of Bunsen burner, and we would have connecting or having the flame just at the top of a rod. Now that rod would be a metal rod, because metals we know are actually really good conductors. And what we'll do is we have Vaseline and wee bits of pins, and we stick the Vaseline and pins at separate distances from each other. Okay? And then we start our stop clock. And we basically time for when each of the little pins falls off. And what you find out, and what we concluded from this, and we're just going to keep this up here so you can see the diagram, is that over time the heat travelled through the solid, and one by one, in the right order, the Vaseline started to melt and the pins then fell off. So we saw that heat was actually traveling through the conductor. Heat was traveling through the metal. And it wasn't just start heating here and starting there, it was heating all the way through. All right? So, our conclusion was this, that conduction is the transfer of heat energy in a solid. Okay? And it's the method of heat transfer we have in a solid. All right. So when particles in a solid are heated, they vibrate. So what was really going on in the physics there was you're heating up one particle, but the next particle beside it, because that one was getting warm, was starting to shake, and that was shaking me. So I would then start to shake the next one, and the next one, and so on until the whole metal was warm. All right. Now that makes sense. Think about if you were to have something like a metal handle and you were heating up like a pot or something like that, you would get burned eventually because the heat would be transferring through the solid. All right, and it's why then we have insulators for things like handles, like kettle handles or pot handles. We don't want to have something that is metal because that's a good conductor. We want something that's a bad conductor, what we call an insulator, and that's things like that's things like glass, wood, plastic. All of those are insulators and protect our hands from being burned because they do not take in heat very well. Whereas metals, for example, in the base of the pot, you do want a conductor because it heats up the food really quickly. So that's us for heat. I hope that was helpful. We talked a lot there about energy transfer, heat, so many things to pack in that wee bit, but I hope that made sense, and you can pause it, remember, look at your notes, go back, rewind it, see if you can understand it, and I hope that helped BGE. Okay, so very well done, and I'll see you in another video. Bye.